Welcome to the Energy Central Power Perspectives podcast. We bring leading minds from the energy industry into the podcast booth to discuss the challenges and trends that are transforming and modernizing our energy system. And a quick thank you to Nokia, our sponsor of today's show. Now, let's talk energy. I'm Jason Price, Energy Central podcast host and director with West Monroe, coming to you from New York City. And with me, as always, from Orlando, Florida, is Energy Central producer and community manager, Matt Chester. Matt, we're recording this episode today in the aftermath of Distributech 2024, where I know you had a chance to chat with today's two guests. How about giving our audience a rundown of what you heard and learned from these two industry pros as a precursor to today's conversation?
Definitely, Jason. And actually, I'd point our listeners to the full interview article that I put together with one of the guests today, which I'll be sure to put a link to in the show notes. But what we spent some time chatting about were the crucial themes of modernization and digitalization in power distribution, particularly emphasizing, the integration of renewables and demand variability management. As we look to the future of increased automation, machine-to-machine interaction in grid optimization, the experts that we're going to speak with today are cautioning against overhyped expectations in areas like AI, but also emphasizing the importance of practical solutions and collaboration for meaningful progress. And overall, I'd say as the power sector moves towards a more resilient and sustainable future, the themes that we focused on at Distributech and that we'll be focusing on today are those of innovation and collaboration.
Thanks, Matt. That's a great appetizer to what is going to be a critical and valuable conversation on the podcast today. And as you mentioned, we're thankful to be welcoming two guests today to dive into some of the key digital utility topics, specifically in the phase of rising cyber threats to the grid. So first, we can welcome on Mauricio Subieta, the Chief Technology Officer of the Energy segment at Nokia. Welcome to the podcast, Mauricio.
Thank you very much for the opportunity. Really happy to be here and answer any questions you may have, Jason.
Fantastic. And joining him is his colleague, Hansen Chan, IP Solution Marketing Manager for Nokia.
Oh, thank you, Jason. I'm very happy to be here. Thanks for having me.
Before we dive into this rich topic of cyber, I want to make sure our listeners really understand each of your roles. So please, I'd love to give you a chance to introduce yourselves even more fully. And Mauricio, why don't we give our audience a bit of your background and what your role is today, and then Hansen, you do the same. How does that sound?
Sure. Like you said, I am Mauricio Subieta. I am the Energy CTO for Nokia. I'm focused on the energy segment and specifically in electric utilities. The focus that I have is on bringing solutions to electric utilities for communication platforms that will enable them to operate their mission-critical networks. I joined Nokia about 8 years ago after working for an electric utility myself. I was the actual network engineer and solutions architect for the networks that were being deployed at the time. And I also was looking into the cybersecurity compliance that has to be met by the electric utilities in the United States. I also was a security engineer while working on that assignment. Before that, I used to work as a network designer and architect for wireless networks, and that's what I've been doing most of my life after I graduated from school.
That is great. Hansen, you want to do the same?
Okay, so Hansen Chan, I'm on the IP solution marketing team for enterprise. I started my career in telecommunications as a protocol test engineer, focusing on bits and bytes of network protocols. Then I became a large network designer or architect, working with carriers around the world. Then I became a product manager for IP, MPLS. And then 10 years ago, I joined the marketing team. I enjoy this role because I enjoy, disentangling a lot of complexity of our product implementation in a way that our users can appreciate and understand the capabilities, and they can use our features to help them work every day. So I really enjoy this work.
That's great. Okay, fantastic. So we brought you in today because of a rather, I would say, interesting and perhaps intimidating topic. It's called the quantum safe network, and we're really intrigued to hear more about it. So how about easing our audience into this complex topic? Mauricio and then Hansen, what exactly is quantum safe network?
Well, a quantum safe network is the one that is capable of sustaining any analysis of the encryption algorithms that are used and potential decryption of such breaking of those algorithms by a quantum computer. So this is something that mathematicians and cryptanalysts have been doing for a long time, trying to find the best way to ensure that the information maintains its secrecy and it is in its integrity by using algorithms that actually use prime numbers and use convoluted mathematical techniques in order to ensure that the message can be encrypted one way and be decrypted on the other end of the transmission line without any potential eavesdropping or additional decoding of that information. So quantum safe computers will allow you to maintain that secrecy even with the advent of quantum computers, which could potentially be used to crack those codes and crack that encryption algorithm mechanism.
Hansen?
I think like a network, right, first and foremost, have to be safe or secure, right? That's why the security team have all kind of tools to make it secure. But with quantum computer, as Mauricio explained, right? So this really changed the game, right? So that's why a whole new consideration, right? And different tools need to be considered, right? To be able to cope with this changing landscape.
Okay. So keep in mind that our audience at Energy Central represents a broad range. So people may not be familiar with some of the terminology. So the term quantum, of course, I guess from a sci-fi sense may conjure up that great show Quantum Leap. But what exactly is quantum computers? Is this term more people are familiar with, and is it being used appropriately in the conversation that we're having today?
I think so. Quantum computing is just like the next evolution of the computing technologies that we're seeing nowadays. We've actually been developing the chips and the silicon for many years, and we had a Moore's law that expected that the power and the performance of a computer was going to double every so many months and many years, or sometimes in so many weeks. And that was just because we were able to miniaturize the components within a computer to more and more smaller scales. Well, there is a physical limitation on that, and there is actually limits that are imposed by physics that you cannot go any better. So the Moore's law has been something of a non sequitur anymore, as it hasn't been meeting its purpose. Enter quantum computers. The quantum computers are based on a completely different type of model, whereas we use bits and electrical sort of signals in the normal computers. Within quantum computers, we use qubits, which are basically particles, subatomic particles in certain states that would represent the information, just as electric impulses would do represent a 0 or a 1. So that, coupled with some additional properties of the actual quantum realm, like superposition and entanglement, make the capacity and the possibilities of computing at a quantum computer significantly far better compared to any computer that you would look at from a traditional point of view. And that's one of the reasons why people are doing a lot of research, because nowadays mathematical requirements for multiple different types of use cases. Think of AI, for example. We talk about large language models that now we can go and use in websites like ChatGPT and applications like those that they have, where a computer can perform many, many mathematical calculations, matrix multiplication operations that will result in answers that are completely based out of this huge knowledge base that will be completely understandable. So the number of operations that can be done with regular computers can be surpassed significantly by a quantum computer. So more and more applications that rely on large mathematical sets of operations, complex operations, they will be possible when the quantum computer become a reality. Right now, quantum computers are still a research topic for many reasons. One of them is the actual complexity of building a computer like this, because of the knowledge required from all the people working on this. Not a lot of people are very much versed in applications on the quantum computers or what quantum computers require, but also because quantum computers are very sensitive of interacting with the regular environment that we know as reality. And as such, they have to be super cool, and they have to be built in an environment in which there's a lot of care on how certain characteristics like coherence or decoherence in the quantum world parlance are maintained. So these are only done by really large institutions and really large universities or research groups that can support such investment. And I don't know, Hansen, if you have something to add to that, please.
Yeah, so maybe I can add a bit color to what you have explained, which is a lot of details, a lot of great details. I think quantum computers started as more of a academic interest, right? This idea of quantum computer was first brought up by a physicist called Richard Feynman, right? So I think his idea at that time was to use quantum computer to simulate a quantum system, which is a very natural, right, use, right? And then, as more, mathematicians come out of algorithms that can make use of quantum computers, the interest in quantum computers, becomes more intense, right? I think one thing that's important, right? So it is very true that quantum computer can perform exponentially, more operations, right, than a classical computer today, right? But the real trick is to find an algorithm that can really harness those power. You cannot just run today's program, on a quantum computer, just like that, trying to accelerate, and speed up the calculations. You need to have a algorithm that can actually use those quantum states, calculation. And that's where the algorithms, comes in, right? And as people, as those scientists understand it better, they come up with different algorithms to solve different problems, especially a lot of those mathematics problems, right? That lead to, where our topic of today, which is encryption. Right. So there are algorithms, being published, right, that can break a lot of those algorithms that we depends on, to encrypt our data.
Yeah, I mean, this is really a complex topic. It's really amazing. Now, tell us about your journey to get here. How did you both get involved and interested in the world of quantum computing and quantum security?
One of the things, as I mentioned, as part of my background, was related to working as a security engineer and as a compliance officer while working in a utility. And to Hansen's point at the beginning, a very important factor of running a electric utility communications network is for it to be safe. And safe because it runs operations that actually could potentially affect the way that we live our lives on a day-to-day basis if somebody were to break into them and basically start wreaking havoc. And obviously, utilities and other industries related to energy are considered critical infrastructure. And as such, they have to meet those requirements of really ensuring that the information and the integrity of the information that they're transmitting, it is there. So that is really where my journey started. It started with the typical cybersecurity IT background of working with firewalls and working with mechanisms to ensure that traffic was safe from a user perspective. But it all then went down as I was working with the utility to cover mission critical operations on a real time basis. And that's really where I found that cybersecurity is quite important. Obviously, having the integrity in our information and the privacy in our information, personal information, records and whatnot, it is very, very important. We see more and more ransomware attacks that are hitting that side. It could be potentially more significant if those bad and threat actors actually jump into a mission critical network like a utility and start making damage or causing damage by affecting the way that the equipment works, which has a definitely cascading effect because imagine schools and hospitals and first responders, all of that infrastructure that we sometimes take for granted really right now works on electricity. So if that is disrupted, everything else is disrupted. So I think that was one of the reasons why I started looking at cybersecurity and as looking into what are the current threats and the potential future threats, because you always have to build a network that will last many, many years. then you look into the topics of quantum safe networking. And I think that's really how I ended up covering this topic and learning a lot of the journey that we have internally in Nokia, just, side by side with Hansen.
So for me, the word quantum has some sentimental feeling. I mentioned Richard Feynman, right, earlier, right? And Richard Feynman, who first proposed the idea of quantum computers, actually happens to be my high school hero. I love physics in my high school days. And then my math teacher pointed to me about Richard Feynman. So I bought actually his book and then read about quantum physics. And then I started to be attracted to quantum physics, for many years. And the topic came up now in the last few years, quantum safe networking, right? And then quantum computer, and then wow, so it really attracted me, and that's why I dive into it, and then and understand more. I enjoy with this work, right? Try to understand and how to help our customer to safeguard against quantum threats.
Okay, so cybersecurity is a major issue across all industries practically. You've done a nice job, both of you, laying out complexities of the industry and the role of quantum computers. Tell us now, why does the presence of quantum computing create a new type of security concern for power utilities? What new vulnerabilities does it introduce, or are there also advantages for the utilities with quantum computing? Let's dig into that, please.
Sure. I think that, like I mentioned just a minute ago, looking at a overall policy of cybersecurity and looking at how to maintain that integrity on the network really involves looking into the future. And one of the things that we've been doing for a lot of years in order to meet compliance for NERC, for example, is to maintain all the traffic always encrypted from an end-to-end perspective. So the threat for that is really related to quantum computers, because as I mentioned really at the beginning, and the question about quantum computers and why they're a threat, it's because those algorithms that are used to encrypt are strong when it comes to supporting any brute force attack, any kind of basically trying to figure out the combination of numbers in the algorithm to decrypt that information from a traditional perspective. Because of the actual architecture of a quantum computer, that task can be significantly reduced in time. Typically, the time that it takes for the current algorithms that are protecting our networks, encryption algorithms, are counted in a large number of years. And when I say a large number of years, we're talking about hundreds of thousands of years. With the actual quantum computer advent, that time can be reduced in multiple orders of magnitude, such that it could actually be used to break encryption in a matter of days, hours even. So it is very important for us to look into how to maintain the integrity of a network, the security of a mission-critical operation network, and potentially also encrypt, protect the data that's encrypted from a different perspective, from the customer information that's in the utility, or from any other type of personal record information that may be held in really anywhere in any other industry. Because one of the things that we're seeing is that just as we are developing quantum computers, we're developing technology that allows us to store a lot of information. And right now, we have almost no limit of how much information we can gather. And potentially that information could be decrypted later. There is this the threat of harvest and decrypt later, meaning that all the information that right now could potentially be of interest can be saved. And then once the quantum computers are available, could be decrypted very easily, such that that information could be also used for not necessarily the right intended purpose, or nefarious purposes, I should say. So I think that is one of the reasons why we look into quantum safe networks, to ensure that even when and if the quantum computers really become as feasible and as adept at doing this type of calculations to decrypt the data, then the information would still remain safe, whether it's a transit or if it's stored somewhere in a static state. Hansen?
Yeah, so maybe I can add a little bit specifics, right? So like the new threat is such that I talked about the algorithm just now, right? So specifically, right? So there's quantum algorithm, like the one devised by Peter Shaw, right? That his algorithm can really solve the factorization of a, humongous prime number. Factorize do a prime factorization of a humongous number to be correct, right? Some encryption algorithm, especially those asymmetric encryption algorithm like Diffie-Hellman, relies on that complexity, right, to do a prime factorization. So which cannot be solved easily, right, even with a classical computer with a large compute power. But now with quantum computer, together with Shaw algorithm, this can be solved. So that means, that public-private key exchange, is now unsafe. It can be cracked easily, right, by bad actors with access to quantum computers, right? So those are the new things, right, that change the encryption landscape, completely, right? So a lot of the encryption package, right, and software, right, are no longer able to protect, communications, right? So we have looked at new ways, right, or new encryption to protect communications.
Okay, both of you have been alluded to new threats, so I'd like to talk about that. Share with us, what are some specific threats coming these days that necessitate elevating systems to quantum safe levels?
The threats that are coming in are basically what Hansen, one of the things that Hansen just mentioned. There's now an algorithm that, if properly employed by a quantum computer, can decrypt the current mechanisms that are being used in the world to encrypt information. So we've seen multiple different types of attacks, starting from ransomware, from massive infections, and also from people that are just going out there trying to store or extract information and extort their owners, not releasing them publicly. Typically, ransomware attacks are related to that one, to the extortion attacks. So those are threats that we see normally on a day-to-day basis. However, in the mission-critical operations, the threats that we see are a bit different. We're also seeing people that basically wanted to hurt somebody or certain population, or they had a grudge and they wanted to basically do some damage. We saw attacks on water utilities, for example, where in the actual plants, the purification plants, more of certain chemicals were added to the water and it made it toxic. We've also seen places that are motivated to actual damaging the response infrastructure, where we've seen turbines being spun at much, much higher speeds than they're supposed to operate normally, creating large damage and even basically destroying the generation plants. In California, we've seen people that go out there and start shooting at transformers, and that was back in the day of 5G, because they thought that 5G was basically hurtful to the bodies, or it was some other type of conspiracy theory. So those attacks are changing. In the specific realm of quantum safe computers, we're seeing more and more people that are trying to find ways to store information that is traversed in the network, especially when it goes through commercial carriers, because it's very difficult now to ensure that all the carriers or all the communication networks publicly available, including the internet, are safe from being completely private. So we see those, and that's one of the reasons why the threats that we're encountering nowadays, plus the reliance on the actual systems to be running 24/7, more so now than before, are making things quite more critical to ensure that their survivability continues, but it also continues in a coherent and consistent manner, that we just cannot assume that there will be burnouts or blackouts that you see sometimes because of high demand in the electrical grid. So they have to be constantly communicating. And that's one of the things that we see as really a key factor for us to be in this segment, specifically providing quantum safe networks to ensure the reliability of the electrical grid, not only in the United States, but throughout all the countries that we serve.
This is podcast producer Matt Chester chiming in again here. The conversation with Mauricio and Hansen was so insightful and in-depth that we didn't want to cut any of it out of the final podcast edit. To make room for it all then, we decided to make this a two-part episode. So be sure to stay plugged into your podcast feed for the second half of this conversation dropping later this week.
We also want to give a shout out of thanks to this podcast sponsor that made today's episode possible. Thanks to Nokia, it's time to start making grid communications quantum safe. Power utilities are extending IEC 61850 enabled automation beyond substations to power the journey to software-centric, data-driven grid operations. But sending IEC 61850 communications over the WAN exposes the grid to cyber threats that put confidentiality, integrity, and availability at risk. The white paper from Nokia, entitled Securing IEC 61850 Communications, explores the major threats to IEC 61850 communications in the WAN, including eavesdropping, and in the middle, denial of service, and future quantum computing attacks. Find out why it's time for utilities to start building a quantum-ready cyber defense and how they can do it with a multi-layer defense in-depth approach that encompasses encryption, firewalls, access control lists, and network segmentation. Download the white paper from Nokia in the show notes or the EnergyCentral.com post for this episode today. And once again, I'm your host, Jason Price. Plug in and stay fully charged in the discussion by hopping into the community at EnergyCentral.com, and we'll see you next time at the Energy Central Power Perspectives Podcast.